Well, thank you, Sally, for the very kind introduction, and thank you for coming. I would like to talk about part of our work in controlling thermal radiation, both from a fundamental as well as from a practical point of view. But before I start, I guess just as a bit of a background on my group work on electromagnetic, and so we study electromagnetic wave and its implication. And now the typical thing that you think about electromagnetic wave, for example, your cell phone communicate through electromagnetic wave. So traditionally, electromagnetic wave has been very widely thought of, and it really is true, as the primary information carrier of the world. But one of the important points that need to be emphasized is that the same electromagnetic waves are also the primary energy carrier. And that really spans from a very wide range of electromagnetic spectrum, going from low frequencies in the range of maybe megahertz or gigahertz. And one example that you know is a microwave oven, where you use gigahertz electromagnetic wave to heat things up. So that's really quite important for energy transmission. And then going up into frequency of electromagnetic wave, you have the thermal radiation, which is the main subject of the talk that I'm going to give here. This you, of course, know if you stand in front of an oven, and much of the heat of the oven will come to you in terms of thermal radiation. And finally, if you go to the visible wavelength range, you would, of course, have the sun, which is the primary energy source for our world. And all those energies come to Earth through electromagnetic radiation. So given the importance and really the ubiquity of electromagnetic radiation for carrying energy, the capability to control electromagnetic radiation certainly should play a very significant role in energy technology. So in my group, we have worked on a diverse range of topics related to control of electromagnetic radiation for energy. At the low frequency side, we work on wireless power transfer using electromagnetic field. We work on control of thermal radiation, and that's a subject that I'm going to talk about today. And we also work on trying to enhance solar cell efficiency, again, by controlling electromagnetic radiation and by designing specially designed optical structure. And I'm very grateful that all of these work have been very heavily supported by GSEP with great encouragement. So in this talk, I'm going to be focusing on control of thermal radiation specifically. And I'm going to talk about some of the basic, some of the application side as a start, and then to talk about some of the fundamental opportunities that come about with the possibility of designing optical structure for control thermal radiation. So the first two parts of my talk has something to do with what we call radiative cooling, and which is, as a background, is really trying to use the universe itself as a fundamental thermodynamic resource. So much of energy research in this world has to do with trying to convert heat into useful work, such as electricity. And for that purpose, the fundamental theoretical consideration in physics is what's called the Carnot efficiency limit. This limit basically says that if you want to convert heat to electricity, you would like to have a high temperature heat source. The higher the temperature, the better. The sun at 6,000 Kelvin, for example, from that perspective, is a fantastic heat source. You will also, on the other hand, like to have a heat sink, and that has a temperature to be as low as possible. That also goes into the Carnot efficiency argument. Now, the vast majority of the energy conversion process that people use today use the Earth itself directly as the heat sink. That's at a temperature somewhere on the order of 300 Kelvin. On the other hand, if you go out of this room and you look up in the sky away from the sun, you should in fact see a much better heat sink. The universe itself, of course, has a temperature that's much lower. That's on the order of 3 Kelvin. So being able actually to develop the universe itself as a heat sink, therefore could have a broad range of impacts on energy technology. And that's really what, on the application side, what we'd like to talk about today. Now, one of the very important points about electromagnetic wave is that it provides remote wireless access to many of these thermodynamic resources. You actually have never need to sit in the sun to do your solar cell research. And so similarly, you actually do not need to go to outer space yourself to benefit from the existence of the outer space. The black curve here is a transmission spectrum of the atmosphere. And I'd like to draw your attention to the wavelength range of 8 to 13 micron, where the atmosphere is actually quite transparent. That wavelength range happened to coincide with the peak of the 300 Kelvin blackbody spectrum. So consequently, every one of us, which has a temperature somewhere in this range, if you go out of this room, you are actually radiating heat into outer space. And that we do on a daily basis. And therefore, this should become a viable cooling mechanism. And in fact, there has been a technology called nighttime radiative cooling. And the idea here is you take a black emitter, something black would do, you go up to the roof, you surround it by an insulating material, but you allow a sky access. As you do that, the emitter radiating its internal heat into the outer space. But in the meantime, if you surround it with the insulating material, it doesn't get much of the heat input from the environment. So consequently, its temperature is going to go down. Now, it's actually in early experiment carried out almost 40 years ago. It was shown that it's actually relatively straightforward to cool this emitter down to a temperature that's about 13 degrees below ambient in an entirely passive way. So this actually is a technology that's available. Apparently, one of the buildings here at Stanford used this to produce cold water at night. But it has not been a very widely adopted technology for cooling purposes. And there are many reasons that you can think of, one of them being that, well, if you like to do cooling, preferably you would like to do it during the time when the thing is actually hot. And daytime, of course, is a much hotter time than nighttime. So if you like to do cooling, you would like to be able to do this during the day. Now, of course, during the day, you would not imagine bring in a piece of black things to the roof in order to do cooling. And the reason is a very simple one. A piece of black thing is going to be heated up by the sun. So from this argument, you can quite imagine what you would do about achieving daytime radiative cooling. What you would like to do is to create a structure that looks like this, which has essentially zero emissivity in the visible wavelength range so that it doesn't get heated up by the sun. In the meantime, it would be still strongly emissive in the 8 to 13 micron window so that it can still emit the heat out. Now, remarkably, this is the kind of thing that you will be very difficult to find in nature. And therefore, it has been very difficult. There's never been any work that demonstrates this to the degree to allow you to achieve daytime radiative cooling. So our specialty is in designing optical structures with unusual electromagnetic property. Therefore, we set out to design something that looks like this in its emissivity profile. And this is our initial theoretical construction out of a simulation. And in order to provide a broadband reflection of sunlight, we envision a multi-layer structure, in this case theoretically made of magnesium fluoride and titanium dioxide, with a chirped periodicity to give you broadband solar reflection. On top of it, we put in materials such as silicon dioxide and silicon carbide with thickness on the order of micron thick. Now, these materials have lattice vibration. For example, in the silicon dioxide, you have vibration between the silicon atom and the oxygen atom. And the resonant frequency of those oscillations happen to be around the thermal radiation frequency. So consequently, they have strong thermal radiation, and putting a grating or a periodic structure on top further enhance such thermal radiation. So combining these structures or materials together, then you can get an emissivity profile that looks like this, having very low emissivity in the solar spectral range and high emissivity in the thermal radiation wavelength range. So this satisfies the theoretical condition that we talk about for radiative cooling. Now, for a cooler like that, there are two important metrics about its performance. One of them is something called equilibrium temperature. So what you envision is an experiment where you take this cooling device, bring it on a roof, surround it with insulator material, but allow it sky access, and therefore it sees the sun as well. In this case, it reflects most of the sunlight and therefore doesn't get heated up by the sun, but in the meantime, it radiates the heat out, so its temperature is going to go down. And using the spectrum that I've just shown you, both the emissivity spectrum as well as the transparency spectrum of the atmosphere, you can compute what the equilibrium temperature will look like. And for a 300 Kelvin ambient, the equilibrium temperature is on the order of 260 Kelvin, theoretically. So to translate into everyday experience, a 300 Kelvin, of course, is a very hot day. So on a hot summer day, and on the roof, when you are facing the sun, a cooler like that actually has the potential to generate ice without electricity. And that's a very unusual potential for these kind of structure. Alternatively, since the cooler itself has a temperature below ambient, you can put a heat load on. And as you put a heat load on, its temperature is going to rise. And you can ask, well, how much heat can I actually put on the structure in order to bring its temperature back to the ambient? And it turned out that the power that you can put in, which therefore is a measure of how much cooling power you have, is on the order of 100 watt per meter square. And 100 watt per meter square, of course, is a non-trivial amount of power. Order of magnitude-wise, this is comparable within the same order of magnitude for solar power. So you're talking about a solar scale kind of application. The United States is spending 15% of its building energy consumption into air conditioning. So being able to reduce this would have a significant impact in United States as well as in global energy consumption. So these are some of the theoretical predictions. Motivated by these theoretical predictions, we then undertook experiments to try to demonstrate it. The initial experiment is a reproduction of the nighttime radiated cooling that people have done, just to show you that cooling can actually be done. So in this experiment, we have an aluminum layer as a reflector with a silicon dioxide layer put on top. It's a very simple structure. And in a relatively warm summer night of about 13 degrees Celsius here, you can get a temperature at freezing. So one really can get to about 13, 15 degrees Celsius, as people have previously pointed out in the literature. Daytime cooling, on the other hand, require a more sophisticated structure. And so using a numerical optimization, we have further simplified this design. And the resulting is now just a multi-layer structure. It consists of 7 dielectric layers made of silicon dioxide and hafnium oxide sitting on a silver mirror that was deposited on a silicon substrate. The top 3 layers here has a thickness on the order of hundreds of nanometers, and these are primarily for emission purposes. The lower layers here have a thickness on the order of tens of nanometers. These, together with the silver underneath here, produce a mirror that has very strong reflectivity. So under white light, this is a fairly good mirror, so it reflects all the sunlight. And if you look at the measured spectrum, it has very low emissivity throughout the solar spectrum, and yet has an emissivity peak in the 8 to 13 micron window. So we then bring this on top of the Packard Electrical Engineering building. So this is the picture of the setup. We tilt the sample to the south, towards the sun, because we would like to be able to demonstrate this in the worst possible scenario, so to get as much sunlight as possible. In reality, if you like to operate this, you don't have to do it this way. You can put it flat, and the performance, if you do it right, would have been better. So one of the things that's quite important about the roof is that the roof is actually a very hot place. Anything that's on the roof under the sun get heat up. So as a result, everything that you look here actually has a temperature much higher than the ambient air temperature. Our objective here is to use this cooler to get to a temperature below ambient. And so this is, roughly speaking, like trying to demonstrate cooling in an oven. And as a result, a lot of effort has been put in the thermal design in order to get this thing to work. Now, there are quite a few advances, and one of them is to design a transparent box around the sample so that nothing in direct contact with the sample actually get heat up at the sun. And the use of a low-density polyethylene to cover the opening of the sample, and that provide radiative access. It's very transparent to infrared light, but in the meantime, it cuts down convection. And low-density polyethylene turned out to be basically kitchen plastic wrap, so we have quite a few of those. So with a setup like this, we can then measure a number of different things in its temperature under the sun. For example, you can put black pans there, and not surprisingly, the temperature very quickly rises up to 80 degrees Celsius, and that's, of course, how solar thermal things work. Somewhat more interestingly, you can put a piece of aluminum there. Aluminum is a pretty good solar reflector, maybe up to 90% reflectivity. But even that's not enough to give you any cooling. In fact, the temperature of aluminum is still about 20 degrees Celsius above the ambient air temperature. On the roof, the cooler that we have is the only structure that has a temperature below ambient. And this is a blow-up view of the experimental data. The green curve here is the solar irradiance instant upon the structure. It peaks around 890 watt per meter square around noontime. The black curve here is the ambient air temperature. The blue curve here is the temperature of the radiative cooler. And you can see a temperature difference below the ambient by about 5 degrees Celsius. So you really see significant cooling here. One of the very interesting things actually occurred in the very beginning of the experiment. So when we start the experiment, the cooler is covered. And therefore, it doesn't see the sky and has a temperature that's comparable to the ambient air temperature. Now, when we take out the cover, for most of us, the everyday experience has been that if you go out into the shade, out of the shade, into the sun, well, you see the sun and you will be hotter. The radiative cooler actually does exactly the opposite. When it sees the sun and therefore sees the sky, its temperature drops very quickly. And that, of course, is a key experimental signature of radiative cooling. Radiative cooling requires you to have radiative access to the outer space. And in this regard, you can see that exposed to the sky lead to the temperature drop. This is a measurement of the equilibrium temperature. We've also done cooling power measurement. And in this case, without putting any additional heat load, the sample will have a temperature with a temperature on the order of -4 to -5 degree below ambient. And as you put a heat load on, its temperature rises. And the amount of heat load that we need to put in order to bring the object back into the ambient air temperature is 40 watt per meter square. And that's the cooling power we actually experimentally measure. So this is a proof of principle demonstration, it certainly is not what the theoretical limit of the performance of these devices can be, and in fact can do a lot better. So at the moment, we're trying to further improve upon this, as well as to scale this up. At the moment, we have an 8-inch wafer, and we're trying to scale this up into enough area to cover some part of the roof to demonstrate actually an air conditioning system. On the other hand, the ability to use the universe itself, which is really a very ubiquitous resource that we all have access to on an everyday basis, should be quite important for many other applications as well. So in the second part of my talk, I'd like to talk about a somewhat different application, again, using the universe itself, and that has something to do with the cooling of the solar cell. So as a background, I hope I've shown you enough experimental data to convince you that roof is a very hot place. And solar cell, remarkably, does not really sit in an air-conditioned room under a solar simulator in somebody's lab. It actually sits on a roof. And therefore, practical solar cell actually operates at a temperature much higher than the ambient air temperature. A typical number that people quoted can be somewhere on the degree of 50 to 55 Celsius. This has a very severe consequences for the properties of the solar cell. Its efficiency degrades as the temperature go up. In fact, a 10-degree increase for silicon solar cell will roughly translate into a 1 percentage point drop in its efficiency, which is really an astronomical large number of efficiency lost in the solar cell context. The lifetime also, with a 10-degree increase, also decreased by about a factor of 2. So operating the solar cell under high temperature cuts down both its efficiency and increases cost, which is highly undesirable. Yes?
Why does it decrease lifespan?
I'm not sure about the microscopic reason, but some of these material probably doesn't last as well. Okay. So now, so therefore, one thing that we see about solar cell is that it naturally has sky access. You need to see the sky. And therefore, it would be very interesting to try to exploit the sky itself as a cooling mechanism for solar cell. So for that purpose, we examine the absorption properties of silicon over both the solar wavelength range as well as the thermal wavelength range in the 8 to 13 micron. In the solar side, of course, it's strongly absorbed. And it's also a weak absorber in the thermal radiation side, and therefore it doesn't have strong emissivity. So a silicon solar cell by itself, a silicon layer by itself, has actually relatively weak of thermal emission and will not cool by itself. In order to do radiative cooling, what you would like to do is to put something on top of it that does not affect the absorption of sunlight, because you are going to try to convert these sunlight to electricity, but in the meantime, significantly increase the emission of the overall structure in the 8 to 13 micron window. So one material that one can use is silica. As I mentioned, silica has a strong thermal radiation and also is transparent. And so you can imagine putting a thick layer of silica on silicon. As you do that, it doesn't affect the absorptivity of the silicon region much. It does enhance the emissivity in the 8 to 13 micron window. But a silica structure like this is actually suboptimum. There is a strong phonon-platon response of silica, and as a result, there's a large index mismatch between silica and air, and so there's actually a strong reflection at the silica-air interface, leading to a substantial dip in the 8 to 13 micron window. Instead, what you would like to do is to structure the silica layer, and in doing so, one does not affect, again, the absorptivity in the solar side. in fact, it slightly enhances the absorptivity because of some of the light trapping effect of the silica layer, but you can bring the emissivity of the structure to be near unity in the 8 to 13 micron window. So these are some of the theoretical simulation. Now to really see how this translates into thermal performance, we perform simulation integrating optics and thermal simulation. So in this case, we take a structure and then instant sunlight onto it, compute the amount of power that get deposited into silicon, and then we then solve, and this is done by optical simulation. We then do thermal simulation where the solar power is then a heat source, and also we put in a convection on the top layer and a conduction on the lower layer in order to simulate some of the other heat loss mechanism in the solar cell. So with that, we can compare the performance of 3 different structures: a silicon layer with a thick silica layer on top, and a silicon layer with a structured silica layer on top. And we plot the temperature of these structures as a function of heating power. So on the order of 800 watt per meter square of heating power, what you see is that putting a thick silica layer on top reduces the overall temperature by about 15 degrees Celsius, theoretically. And there's another 5 degrees Celsius gain to be had if you replace the silica flat layer with a structured silica layer. So the efficiency improvement estimated, if you can lower the temperature by this much, would be more than 1 percentage point, which is very significant in the context of silicon solar cell. So we have done some initial proof of principle demonstration experimentally. And in this experiment, as the baseline, we take a silicon wafer that people routinely use as a starting point for solar cell. So this is the same silicon wafer solar cell with a silicon nitride anti-reflection layer that people put in. And then to cool this down, we compare 2 structures. One of them is a silica structure, a 500 micron thick silica structure. And the other one is a silica photonic structure that we measure where we etch into the silica structure. This is the SEM image of the silica photonic crystal. It has a square array of air holes etched into silica. The periodicity here is on the order of 6 micron because this has to match with the thermal radiation wavelengths around 10 micron or so. So these are some of the optical and thermal spectral properties of these structures. On the left here is the absorptivity as a function of wavelengths in the visible and near infrared. And you can see strong absorption of all 3 structures in frequency above silicon band gap, as you expect. The absorption property of all 3 structures are actually fairly similar. And in fact, the photonic crystal structure has a slightly higher absorptivity compared with the bare silicon region due to the light trapping effect I've been talking about. Even though they have very similar visible or near infrared spectral characteristic, their properties in the far infrared is actually very different. The black curve here is the emissivity of silicon, bare silicon layer, and you can see the emissivity is relatively low. The blue curve here is the emissivity of the structure consists of a thick, uniform 500 micron thick layer. And as theory predicted, you indeed would observe a very strong dip in the 8 to 13 micron window, indicating that this is suboptimum as far as trying to emit thermal radiation in the 8 to 13 micron window is concerned. The red curve here is the emissivity of the silica photonic crystal. And you can see near unity emissivity over the entire thermal wavelength range. So in this case, the silica photonic crystal that we fabricate actually is a visibly transparent thermal blackbody. And that is, I think, a somewhat unusual concept because most of the blackbody, thermal blackbody you can think of are, of course, black. So again, we perform a rooftop experiment to demonstrate the cooling performance. So in the first experiment, we basically take the same, very similar setup as we did with the daytime radiator cooling experiment. We put these wafers in. We cover each of these boxes here with low-density polyethylene to cut down the convection, and we measure the temperature under the sun. So you can see that by putting a silica layer on top, you have a significant temperature reduction as compared to the bare silicon wafer. And moreover, out of the three structures, the photonic crystal structure has a consistently lower temperature compared to all the other structure due to the enhanced thermal radiation coming from the photonic crystal. So one indeed sees the possibility of significant radiative cooling for a solar absorber structure. In this experiment, we have put a polyethylene film to cut down the convection. The temperature that you have here, because the structure absorbs the sunlight, by necessity is above the ambient. So because the temperature is above the ambient, one can actually combine radiative cooling with convective cooling. And to do that, what we do is we simply remove the polyethylene film that cover the entrance of the box. As we do that, the temperature of all three structures drop because now you have convective cooling. But the photonic crystal structure still have consistently lower temperature compared with the bare sample as well as the planar silica sample. And this again indicates the possibility of using radiative cooling together with more conventional cooling mechanism for solar cell in order to lower the temperature of the solar cell. So up to this point, I have mentioned some of the more applied work, of course somewhat unusual applied work, but applied work on controlling thermal radiation. What underlies this is really the capability to design new photonic structure or new electromagnetic structure in order to create thermal radiation properties that are very different from bulk material. So in the very last part of my talk, I want to continue on this theme by pointing out some of the recent work where we really try to design these photonic structure in order to advance the control of thermal radiation in the basic and fundamental way. And one thing that I'm going to talk about is the ability to actually overcome one of the basic limitations in thermal radiation control in terms of the Kirchhoff law or the detail balance. So this is actually one of the fundamental law of thermal radiation control in almost every textbook. And it basically says if you have an emitter, then the angular spectral absorptivity when light is coming from a particular direction at a particular frequency and a particular angle has to be equal to the angular spectral emissivity in the same frequency and the same angle. Okay? And this is sometimes referred to as the detail balance for these systems. And it is satisfied for the vast number of emitters that one have in this world. Now, this actually provides a fundamental constraint on many of the performance of solar and thermal absorber. For example, in the case of a solar absorber, it has to absorb the sunlight from the sun. So by detail balance or by Kirchhoff law, then high absorption from this direction necessarily imply strong emission back in these directions. So as a result, the detail balance actually gives you an intrinsic loss mechanism for many of these absorbers. Now, it would be a lot nicer if instead the emission doesn't have to go back to the sun, but instead can be rerouted elsewhere so that you have a second chance of getting energy out of these thermal radiation. Now, and in fact, there has been significant set of theoretical work showing that the fundamental limit of solar energy conversion will get very significantly improved, going from like 85% to 93% efficiency. These are theoretical limits if you can break detail balance. Now, one of the very important points to emphasize is that detail balance is actually not a second law requirement. It's actually not required by the second law of thermodynamics, but rather come from the fact that most materials in the world are reciprocal materials. And in fact, if you can break reciprocity of these materials by applying a magnetic field, for example, you could actually break detail balance. So, to review that, it will be useful to consider a standard reciprocal lossy medium. All the structure I've talked about up to now, for example, are standard reciprocal lossy medium. And then imagine these are in thermal contact, radiative contact with two black bodies. And if you have a black body A emitting down, you have a reflectivity to black body B here. And if a black body B here emitting down, we have a reflectivity to black body A. Then the reciprocity will require that these two reflections are actually the same. And so consequently, actually you can show that the emissivity and absorptivity has detail balance. On the other hand, if one were to break reciprocity by applying magnetic field, for example, into some of these structures, then the reflectivity along these directions may actually be different. And in this case, one can actually show that the emissivity and the absorptivity between these emitter and the black body actually would be different as well. So breaking reciprocity will actually allow you the possibility of breaking detail balance. Now, having said point out the basic possibility of breaking reciprocity, if one wants to be able to implement an energy conversion scheme like this, what you would like to do is actually to completely reroute the emission elsewhere. So what you would need is actually a maximum violation of detail balance. In other words, you would like a unity absorptivity along a particular direction and a zero emissivity back to the same direction. And that actually has never been done before. So what we do as numerical work was to show that you can actually design photonic structures to achieve that. And the idea here is to take a low bandgap semiconductor, applying a magnetic field, and as you do that, you have a dielectric tensor that breaks reciprocity. And in this case, when you look at light reflected coming from these two directions, these two directions that are related by reciprocity actually will have a split in its emissivity profile, in its reflectivity profile. And consequently, when you compute the absorptivity and emissivity of the structure, you will also see a split in the absorptivity and emissivity. So there are actually wavelengths where you have near unity contrast between absorptivity and emissivity in these structures. And that, we think, is important initial step in really trying to design something that breaks reciprocity in order to gain access to some of the thermodynamic potential that has not been available in most of the other structures. So with that, let me briefly summarize. I hope in this talk to convey to you that there are really very significant practical possibility for controlling thermal radiation for energy conversion possibilities. And moreover, what the modern technology affords you is really the possibility to create structures which allow you to fundamentally rethink about what thermal radiation property should look like, and therefore to create new functionalities. With that, let me acknowledge the students and research associates that have done the work. In particular, Ashwat Raman, who is sitting somewhere there at the back, who has been really the leader in doing many of the radiative cooling work that we're talking about here, as well as Lin Xiao Zhu, who has done a lot of work on solar cell cooling, as well as on the non-reciprocal thermal radiation. So with that, let me stop and thank you for your attention.
So I'll help you with questions, yeah? Okay. Okay, questions, starting with the students. Okay, yeah, way in the back there, yep.
Are any of these methods commercially available?
Sorry?
Are any of these improvements commercially available?
Not yet, not at this point, but we're working towards it.
Okay, how about some more? Hold on, we'll see if, okay, yeah, how about you?
So what you're saying is your name is technologies.
I think certainly we would need to scale this up and coupling it with, for example, coupling it with an actual cooling system. So in my mind, it's a matter of doing it.
Is there any work being done, I just thought about this, instead of radiative cooling, kind of reversing the process for like a heating?
Certainly, solar thermal has been done very extensively, if that's what you meant. And there, the actual design, the spectrum will look exactly the opposite, like our radiative cooling. So you like actually strong absorption and no thermal emission. To do that well, actually, is non-trivial.
Is there any concern about placing like highly reflective materials on a roof with air traffic or anything flying over? I didn't know if that was a concern for the research.
No, because it's not a concentrated situation. The best that you are getting is a factor of 2, right? Because you are basically standing in front of a mirror.
All right, some more. No more students, at least for now? Oh, okay, how about you? Yeah.
So,
Not a statement.
You're okay.
can I go now?
Yeah, you can go now.
So at the beginning of the talk, you had this picture, I think it was from an Ohio State astronomy picture.
Right.
Right, where you showed the absorption lines of water and ozone in the atmosphere, right?
Yeah.
So I'm wondering if that was specific to the humid air in Ohio, or does it work to the drier air in California?
Oh, in fact, even though it's Ohio State picture, it was taken on top of one of the mountains in Hawaii where they have a telescope. Yeah, where the Mauna Kea, yeah, where the air is extremely transparent. So in Palo Alto, this is more typical. The green curve, the blue curve here is more typical in Palo Alto. So some of the main differences are when you come to California from Hawaii, some of the best places is that the emissivity actually goes down, the transparency goes down in the 8 to 13 micron window. And also the secondary transparency window actually disappeared. So the data that I show you, if we could do the experiment there, would have been a lot better. Yeah.
Okay, all right, yeah.
How much more difficult was it to make the photonic structure out of the silica as opposed to the planar surface?
You mean for the radiative cooler structure, the beginning structure that I showed? Silicon is a completely inert in this, so it's just convenience. In fact, the functional structure is from silver up. The rest are just substrate. It happens that, well, when you start, you look for the most convenient place to fabricate your structure, and fabricating on silicon is most convenient. There's no intrinsic reason for doing so.
Okay, all right, okay, we'll go over there and then here and then back there. Okay, we'll start with you, yeah.
That's the thickness of this layer. It seems like a highly optimized structure. And
Yes.
I was wondering how optimized it is and how much parameter space you can still investigate in order to make it simple and maybe cheaper to produce in larger scale.
Since this is just a thin film deposition, in principle, this can be directly applied to large scale. As far as optimization is concerned, these are optimized within the constraint of a particular vendor that we use to fabricate this. So it's certainly by no means an optimal structure. In fact, optimal structure would have a, so for example, you look at the emissivity here, it's only on the order of 60 to 70%. And certainly there's a room to improve it further. And even within the constraint of multi-layer film, so they can do just thin film deposition without lithography, one actually can improve this a lot more.
Okay, we'll come over here. Yeah.
So optical isolators use that same kind of
Right.
non-reciprocal. So can you use, I mean, putting magnets on your rooftop doesn't seem so practical, but is the Earth's magnetic field strong enough to be able to do that or not?
That's an interesting point. My quick guess is no, but I don't know. That would be nice. That would be very nice. Yeah. So one should work on better magneto-optical material.
Yeah,
Maybe
yeah.
that's the question, is whether you can. Yeah, that would be very nice. Yes.
Okay, all right, yeah, you open this up.
With 0.35% per degree C degradation of current photovoltaics, what limits you to not getting, say, 10% efficiency increase?
You don't. Well, it's 0.45% relative. So that translates into about 10 degree, or for 20 percentage solar cell, 20 percentage point efficient solar cell, that translates into about 1 percentage point per 10 degree.
Okay, but you get
Yeah.
10 or 20% more.
Relative, yeah. Yeah, you get 10 to 20 percentage point relative. You don't get 10 to 20 percentage point efficiency improvement. I think that would be good. Yes,
fabulous.
that would be fabulous. Yeah, that you should do the Earth's magnetic field idea.
Okay, more questions? No? Okay, sure, here, right there.
I'm interested in how the temperature was measured, both in the ambient and on your device.
Okay.
Of course, at nighttime there's no sun, and so therefore the temperature doesn't change, and so you can make
Yeah.
a very consistent measurement.
Yeah.
But during the day, you have the sun that forms an arc, so it's
Right.
changing the temperature constantly. And are there non-equilibrium effects on the device? I'm sure you've already checked this.
Yeah, so the temperature of the ambient is measured by under the shade. Under the shade, but outside the box. And the temperature of the sample itself is measured by thermocouple at the backside of the sample. And if you look at the data itself, what you do see is substantial temperature fluctuation both in the ambient air temperature and the radiated cooler temperature. As far as non-equilibrium effect is concerned, in this case, the thermal insulation is still not perfect yet. So in fact, the response of this is very fast because there's still a substantial heat leakage from this into the ambient. So you can see, for example, you may probably infer some time constant measure from here.
You did this and you averaged the results over several days. Do you have the results we could see for that?
I don't have it with me. Now, the result depends quite a bit on the air quality. And this was done actually in December of 2013. Both of these data were done. I showed both of these data, but 2 separate days. So you can see actually the temperature is slightly different. Those few days happen to be have a very low dew point, that the transparency of the air is particularly good, which we didn't know. We learned it later.
That makes
But
a huge difference.
that makes a huge difference. So this is a technology that does depend on the weather.
Okay, and we have one more right here, yeah?
Are you looking for, is your next step from here to look for new materials that exhibit similar properties, but to an even better extent?
We are certainly trying, so there's no reason why we're restricted to silica and hafnium oxide. There's just no reason for that. So some of the other material that we're trying potentially has higher emissivity in the 8 to 13 micron window. And we are actually trying to demonstrate some of those experimentally as well.
Okay, oh, one more, yeah.
A quick question. The transmission spectrum of the device is measured without the thermal isolator, like the film on the top, correct? In lab?
You mean the last part of my talk, or?
No, just related to this.
Oh, you mean the transmission spectrum of the atmosphere?
Of the device that you've made.
I don't think we, it's meshed, these are the entire structure. So these are absorptivity measurement. Okay. Absorptivity measurement. So it's absorptivity for the structure itself.
Correct, like in the lab, not on the roof.
No, right, in the lab. Yeah.
Like so without the film on the top.
Without the film on the top, yeah.
Yeah, because that's for thermal.
Yeah, the film does cut down a bit of the, it's not 100% transparent. So it does cut down on the transmissivity, on the thermal emission.
Okay, all right, well, thank you so much.